how many different colors do you see here? Right, it's 2. What about here? This one's a little bit harder, but you can still tell there are 7 different colors. But what about here? You could figure it out if you stared at it long enough, but it's starting to get time-consuming. And if we want to be efficient, we should probably design some kind of counting algorithm and get a computer to run it. At this point, the simplest algorithm we could implement would look something like this. We initialize a counter to 0, line up all the circles in a queue, and process them one by one as they come in. Every time we see a circle with a color we haven't seen before, we increase our counter by 1. And if the color is one we've already seen, we simply ignore it and move on. If we ever want to know how many distinct colors we've seen so far, we can just look at the counter. But here's the catch. In order to know whether a color is new, we need to keep a list of all the colors we've seen so far. And we need to check that list every time a circle arrives to see if its color is already there. That's manageable when there aren't many colors, but as the number grows, the list takes up more and more space. So while this method works, it's not exactly efficient. It needs O of n space where n is the number of distinct colors. The question is, can we do better? Can we reduce the amount of storage we need while still getting a good sense of how many distinct colors there are in the stream? That's where the HyperLogLog algorithm comes in. It gives us a solid estimate using far less storage, as long as we don't need an exact count. For example, the output of the algorithm might say something like, there are about 1.3 million colors, plus or minus 10,000, with 90% probability. So it gives us an estimate rather than the exact count, but the result could still be useful, depending on the application. To get a feel for how HyperLogLog works, let's start with a simpler example. Imagine I pick n numbers between 0 and 1 at random, but I don't tell you what n is. Then, I generate a stream of numbers by sampling from these n numbers over and over with replacement. Your job is to study the stream and come up with an estimate for n. How would you do it? Well, one thing we can take advantage of is the fact that the n numbers are uniformly distributed between 0 and 1, which turns out to be an incredibly powerful assumption. It turns out that if you have n independent numbers, all uniformly distributed between 0 and 1, the expected distance between any 2 consecutive numbers is 1 over n plus 1. That tells us that the expected value of the smallest number is also 1 over n plus 1, or in other words, that we can approximate n as 1 over the smallest number we see in the stream. Here's what a rough algorithm would look like. As numbers come in, we just keep track of the smallest one we've seen so far. Then, when we want an estimate for n, we can simply return 1 divided by the smallest number. The key thing to note here is that we don't need to remember all the numbers we've seen so far, just the smallest one, which makes the algorithm more efficient. But what if the elements in the stream aren't numbers at all? What if they're colors, or IP addresses, or user handles? Well, in that case, we need a way to turn each element into a number that looks like it was sampled uniformly between 0 and 1 so that we can apply the same trick from before. This is where hash functions come in. For our purpose, the hash function is simply a function that takes an element and turns it into a fixed-length bit string in such a way that the same input always gives the same output, different inputs give different outputs, and the bits behave like independent fair coin tosses. The reason hash functions are useful in this case is because we can turn any bit string into a number that looks like it was sampled from a uniform 0-1 distribution, which in turn gives us a way to convert our stream elements into numbers that look like they came from a uniform 0-1 distribution. This turns the problem of counting colors into something we already know how to do. But how do we actually turn a bit string into a decimal number? Let's look at an example. Imagine we have a 6-bit string with the bits labeled B1 through B6. We can convert this into a decimal number like this. Here's an easy way to think about it. Starting at 0, each bit has a weight that tells us how much to add. The first bit has a weight of 1/2. If the bit is a 1, we add 1/2. If the bit is a 0, we add nothing. The second bit has a weight of 1/4. The third bit has a weight of 1/8, and so on all the way to the last bit. when we add up all the weighted contributions, we get a number somewhere between 0 and 1. And because each bit was chosen by an independent fair coin toss, all possible numbers are equally likely. That means that the resulting number looks like it was drawn from a uniform distribution between 0 and 1, or to be more precise, between 0 and 1/2 to the number of bits. But if the number of bits is large, this last small chunk is negligible. So hash functions effectively let us map our stream elements to decimal numbers, and now we can rely on the same trick from before to estimate n. Putting it all together, the algorithm looks something like this. As elements arrive from the stream, we first hash each one into a bit string. Then, we convert the resulting bit string into a number between 0 and 1 using the formula from before. As we process elements from the stream, we keep track of the smallest number seen, and just like before, whenever we want an estimate for n, we return 1 divided by the smallest number. This algorithm works, but there's a neat trick we can use to make it even more efficient. It turns out we don't need to convert the bit strings into a number. We can skip that step entirely and still get the information we need. Let's walk through a quick example to understand the idea behind this trick. Imagine we have two bit strings, A and B, and we reveal only the first bit of each. Both bits are 0. Can we tell which number is smaller? Well, no, not really. All we know is that both A and B represent a value between 0 and 0.5. Now, let's reveal the second bit. Now we see that A represents a value between 0 and 0.25, and B represents a value between 0.25 and 0.5. So, even though we don't know the other 4 bits, we know A must be smaller than B. This illustrates the key idea. The more leading zeros a bit string has, the smaller the decimal number it represents. Let's say the longest run of leading zeros we've seen so far is 4. That gives us a clue about the smallest number in the stream. Specifically, the smallest number is between 1/2 to the 5 and a slightly larger upper bound. So we can estimate that the smallest number is approximately 1/2 to the 5. In this case, the smallest number is estimated to be about 0.031 when it's actually 0.046. In general, if r is the length of the longest run of leading zeros plus 1, then the minimum number is approximately 1/2 to the r. And here's the cool part. Since our estimate for n was 1 divided by the minimum number, this means that we can roughly estimate n as 2 to the r. And this logic works no matter the length of the bit strings. For example, if we have a stream of 16 bit strings and the longest run of zeros we've seen so far is 7, then r is 8. The minimum number is about 1/2 to the 8. And our estimate for n, the number of distinct elements, is 2 to the 8. This approximation means we can simplify our code because instead of converting each hash bit string into a decimal number, we can just keep track of the longest run of leading zeros. Tracking the longest run of leading zeros gives us a way to estimate the smallest number in the stream and, from that, the number of distinct elements. But at the end of the day, this is just an estimate, and because the hash bit strings are random, the estimate is also random. One way to tame this randomness is to turn to the central limit theorem and try to generate several independent and identically distributed estimates and average them. That would help smooth out the variation and give a more reliable number. So we could think to do something like this. We set up several computers, each using its own hash function. Each computer processes the stream, hashes the elements, and estimates n. At the end, we average all the estimates to get a more stable final estimate. The downside of this approach is that evaluating multiple hash functions for every element in the stream means a lot more computation per element, which can slow things down on large streams. So the question becomes, can we get the benefits of averaging using just one hash function evaluation per element? Well, here's an idea. Our algorithm hashes each element in the stream into a bit string, which you can think of as a number drawn uniformly between 0 and 1. Now, imagine we split the interval from 0 to 1 into m non-overlapping subintervals of equal length. If we have n distinct elements, you'd expect roughly n over m of them to fall into each subinterval. So, what if we get m different computers, assign each to a different subinterval, and ask them to estimate the number of distinct elements within their assigned subinterval? Each computer can then multiply its estimate by m to get an estimate for the total number of distinct elements in the stream. Doing this across all subintervals would give us several independent and identically distributed estimates which we could then average. And as a nice bonus, if one or more of the computers fails, we still have several estimates we can use from the remaining computers. The way this applies to our case is that we can hash each element once, route the resulting bit strings to the right computer based on where they fall in the unit interval, and let each computer come up with an estimate for n. We can then average the estimates to reduce variance, still using just one hash function evaluation per element. Now, the obvious way to figure out which subinterval a bit string belongs to is to convert it into a number first. But it turns out there's an even easier way to route the bit strings. The idea is fairly simple. If m is the number of subintervals, the first log of m bits of a bit string tell us exactly which subinterval it falls into, because all the elements in the same subinterval share the same first log of m bits. In other words, we can use the first few bits of the string to route it to the right computer without needing to convert it into a number first. Now, if you're one of, say, m equals 8 computers, you'll receive a substream of bit strings where the first 3 bits are the same for all strings, but the remaining bits still look like fair coin tosses. Your job is to estimate the number of distinct elements in your substream and multiply it by 8 to get an estimate for n. Here's where you might think to use the same estimation approach from before based on the longest run of leading zeros. However, that estimation approach only worked because we assumed all bits were fair coin tosses, because that's what guaranteed that the hash numbers behaved like uniform values between 0 and 1. But here, the first few bits aren't random at all. They're fixed for every element in your substream. And at first that might sound like a problem, but it actually isn't. Those fixed bits don't tell us anything about how many distinct elements we have in our specific substream, so we can actually just ignore them. The important part is that the remaining bits still capture the distinct number of elements in our substream and still behave like independent fair coin tosses. So we can just apply the same longest run of zeros idea to the random tail of the bit strings and multiply the resulting estimate by 8 to get an estimate for n. This is the basic idea behind the HyperLogLog algorithm, which makes 2 additional modifications. Instead of combining the estimates from the different computers with a simple average, the HyperLogLog algorithm uses the harmonic mean because of its tendency to dampen noise in the estimate. The HyperLogLog algorithm also scales the final estimate by a factor to remove statistical bias. At this point, you might be wondering why the algorithm is called HyperLogLog in the first place. Well, the first log comes from the fact that for n distinct elements, the maximum run of leading zeros you'd expect to see is roughly log of n. In other words, the maximum r is roughly log of n. The second log comes from the fact that storing the maximum run of leading zeros requires log of r bits. The hyper part refers to using the harmonic mean and to a few other refinements the algorithm makes, and that's how HyperLogLog gets its name. Now, there are a few extra practical details the full algorithm has to deal with, like what to do if n is extremely large and we start running into more collisions in the hash space, or what to do if n is much smaller than m and a lot of the registers or computers end up empty. But the heart of HyperLogLog is still the same clever idea. It's compact, surprisingly powerful, and now you know its core concept.